Color theory. I love color theory. It's my favorite part of the talk. I may put it in more in one section. So we're going to talk today about color. Yay, color. Now, we're not talking about regular color. First, we're going to talk about color inside of computer graphics. Now, back in the day when I was just a young one, there were only two colors, and they were, go ahead, scream it out. Did you say black and white? Because you're wrong. I want you to think about that for a second. I love this part of the conversation because when I do have this part of the conversation, people go for the logical answer. The logical answer is, well, black and white. But really? Think back and close your eyes. And if you're not that old to remember these things, think about old computer monitors, old monitors in movies. What color were the monitors? Now, there are really two answers that might come to mind. One answer would be black and green. Remember those black and green monitors? That green glow? You're also going to see like a black and amber, which is more like a red or an orange. And that's what computer monitors look like. Matter of fact, black and white monitors came much later and they were really, really important. Now, when we talk about this for a moment, it's really important to remember that really, let me try it this way. If you were to turn off your TV, right? Go look at your TV, wherever it is. I have one right over here, so I can look at it, right? What color is your TV when it's off? Of course, you're probably going to look at it and say black. You're probably right. But if you were to look around the room, you'd say, wait a second. Is there something that's blacker than your TV? And you're like, uh-oh. I guess there is something blacker than my TV. Then what color is your TV? It's not really black. It's like a really dark gray. And this comes back into the fluidity of language. But the problem is this, is when your TV is off, you instinctually know that it is dark as it can be. So when you say that TV is black, it's not because you know it's black. It's because it's black enough, because it's as black as it's going to get. So we call it dark gray because if we were, color scientists, we'd go, that's dark gray. But we're like, no, it's black. And so what we're really looking at is an interesting little thought exercise that I'd like you to do. I would like you to imagine for a moment that you're in a room. The room has no windows and no doors. No, actually, if there's no windows, no doors, how do you get in there? But you're in a room with no windows. And hanging from that room is a single white light bulb. What color is the light bulb when it's on? If it wasn't me asking, you'd go, white. All right? Turn it off. What color is it now? Well, you can't see anything. Well, what do you call it when you can't see anything? Black. Now, I have to quickly interrupt because someone is like, black and white aren't, someone's taking too many physics classes. Black and white aren't colors. Black is the... Today we're going to play by what I refer to as Crayola rules. When you buy a box of crayons, you do not get 62 colors plus black and white. You get 64 colors. So if Crayola calls them black and white, we're going to call them that as well. So the idea is when the light bulb is on, it's white because you can see it. And when the light bulb is off, it's black because you can't. Now imagine for a moment that same room, instead of having a white light bulb in there, you have a red light bulb. Now, what color is the red light bulb when it's on? Red, that's what you see. What color is the red light bulb when it's off? The answer is, what do you see? Nothing. So it's black. So the idea is it doesn't matter what color the light bulb is, when it's off, it's black. Very important part of this discussion. So when you look at these early monitors, whether they're black and green or black and amber, really, the light bulbs are green or the light bulbs are amber, but the off is off. They're really one color monitors that can turn off. So when we're dealing with two colors, it's whatever was on and off, this on and off state. So we basically were dealing with two colors. So that's where we started. That's in the olden days. Then, magically, we got to 4 colors. Ooh. Then we got to 16 colors. Now, I'm not going to deny 16 colors is a lot of fun. You can have a lot of fun with 16 colors. And in the world of computer graphics, we did have a mighty good time in the world of 16 colors. But if I were to give you a box of crayons and a sheet of graph paper and say, paint my portrait, not necessarily. So 16 colors is fun, but it isn't photographic. We get to the magical area of photographic color when we hit the number of 256. When we get to 256 colors, we immediately start being able to start seeing things as recognizable. So, do you see a trend in these numbers? You're like, I know, they're even. More than that. 2 to the first power is 2. 2 to the second power is 4. 2 to the fourth power is 16. And 2 to the eighth power is 256. Which is why 256 colors is referred to as 8 bits. 8-bit means 8-bit of something. 8-bit is equal to 256. 256 what? Where are my unit? Well, it's right there. It's colors. 256 colors. There are 256 colors is the same as 8-bit. Now, again, computer scientists came up with this. We are stuck with it. The dangerous part of it is that when we hear things like, that is an 8-bit game engine. Well, 8 bits of what? Again, they don't mean color. Luckily, sometimes they mean color. Some of them mean processor power. So it's very important that when we have these conversations that we don't just throw numbers at each other. We know what those numbers are. So again, if we come over here, if I were to say 2, I'm going to use the caret. 2 to the first power is equal to 2. Oh, look at that. So nice. 2 to the second power is equal to 4. 2 to the fourth power is equal to 16. And 2 to the eighth power is equal to 256. Now, what's nice about this is, and I'm going to leave out the caret for a moment so that we can leave it. I'm going to leave it out the caret for a second on purpose. We know what's coming next, right? We can now take a look at the next part of our equations. So if I were to look at this, and I were to say, what is 2 to the 16th power? Well, 2 to the 16th power is, what was that? 2 to the 16th power is 65,000 colors. And that's a pretty big number of colors. And 2 to the 24th power is equal to 16 million colors. And I'm loving this one. And 2 to the 48th power is equal to a lot. Isn't that great? It's a lot. Now, the cool part is normally what I would say is that instead of saying exactly how many they were, I would say approximately 64,000 colors, 65,000 colors, and of course, approximately 16 million colors, which is really more like 17 million colors. And of course, this is equal to a lot. You don't even have good words for it. They will refer to this as high color, and we will refer to this as true color. And again, a lot. Now, what's nice to know is again, how these numbers come about. This idea that 2 to the 8th is 256 is something you are going to see inside Photoshop and other programs over and over again. And the more you understand why it's using those numbers, the better off you're going to be. The reality of it is that we tend to live right over here in 24-bit colorville. We tend to live in the 16 million color range. The reality of it is that when I talk to people about 16 million colors, that's more colors than the human eye can see. I've been doing these workshops for years, and one day the little old lady in the back of the room goes, "Yeah? Then how do you know they're there?" I'm like, wow, that's a really good question. She goes, "Yeah, I was here last month." And I love that because she actually it really had frustrated her that I had said that there's more colors than the human eye can see. So what we need to do is we need to go a little bit more in depth into how color works. And to do that, we need to reveal to you the lies that you learned as a child about color. So, when you were a little kid, they told you that there were 3 primary colors, and that from these primary colors, you could mix all the other colors. And this is standard art class little kid stuff, and they told you that the 3 colors are red, yellow, and blue. I think I chose a little dark of a blue. And we all know that if you mix red and blue, you get purple. Oops, that's not purple. You get purple. And if you mix red and yellow, you get green. And if you mix red and blue, yellow and blue, oops, that's wrong. Red and yellow, you get orange. And if you mix red and blue, you get yellow and blue, you get green. So these are what we learned about primary and secondary colors. The reality of it is, it's a lie. Don't blame me, but it's true. Let's go back to this a little bit, and let me show you how this works. When you were a little kid, and some of you are going to remember this, by the way. Some of you remember this. When you mix red and yellow and blue all together at the same time, what color did you get? You got brown, didn't you? What color did you think you should get? You're like, black. And that's exactly right. Matter of fact, I always joke because I've been carrying this grudge with me for 40 years, which is why I teach it now. And you can tell though what kind of a kid you were, because if your teacher tried to explain to you that was one thing, if they said shut up kid, here's some black paint, then you were a pain in the ass. I was a pain in the ass. But the problem here is if you mix red, yellow, and blue together, you get brown. And the reason you get brown is because they're not actually spaced properly on the color wheel, because they are not the true primary colors. Who do we blame for this? Well, a lot of people try to blame Isaac Newton, but it really isn't his fault. So what did Newton discover? I always joke about this because people go, gravity. He didn't discover, he didn't invent gravity. He actually did create calculus for whatever reason. That's useful to know. I mean, you'll know that he did it, not that it's useful to know. The idea, though, is that Newton was not the first person to put white light through a prism and get a rainbow. Others had done that before. What Newton had done was he put the rainbow back and created the white light. What's cool about Newton was that somewhere in his writings he said, and if you were to take the rainbow and put it in a circle, this could be useful for artists. He did not say what went where, but people jumped on this and started to create their own circle, their own palette, and their own trying to figure out what goes where on the color wheel. Matter of fact, this happened for hundreds of years. And so Newton sort of started it, but people started creating all these sorts of color wheels. And I've got other historic examples of color wheels. Matter of fact, let me see if I think I have Goethe's color wheel right here. No, I don't. But I've seen it before. But the idea is that the color wheels existed up until color scientists really perfected true color science, and that would be the turn of the 20th century. So, what does true color science look like? Well, let me show you.